Very good evening to all of you, and welcome to this special colloquium. It's my honor to introduce today's speaker, Professor Martin Paetzold, who is a very good friend of mine, and he is visiting PRL. We have a Indo-German project to study the Venus atmosphere through radio science experiments. So I will not go into that because that is what he will be covering in his talk. So he's visiting us for this purpose. Just to briefly tell you about him, Professor Martin Petzold is the president of the Rhenish Institute for Environmental Research at Cologne University. And he is also the director of Department of Planetary Research and a lecturer at Cologne University. So he did his diploma in physics and subsequently he obtained a PhD in astronomy in 1990 from Universitat Bonn. And after that, Professor Petzold obtained his habilitation in geophysics in Germany. Professor Petzold is a world-renowned expert in the domain of radio science experiments for planetary atmospheres. And these are techniques which basically probe the atmosphere and obtain the pressure, temperature, and electron density profiles. And that is what he'll be talking to us about today. And with developing such instruments for various missions, he has studied the atmospheres of Mars, Venus, and other planets, and also the ionospheres of the morphology of ionospheres of Mars and Venus. In fact, particularly, he has discovered the meteoritic layer in the ionosphere of Mars, which forms at a low altitude due to the ablation of meteorites. Professor Petzold has served as PI of the radio science experiments on several interplanetary spacecrafts, such as Rosetta from the ESA, Mars Express from ESA, Lucy from NASA, and Matisse from ESA. And he was also the co-PI of such radio occultation experiments on several missions, such as the Venus Express, which has given a lot of valuable data. Giotto, also from the ESA, Ulysses, New Horizons, and also the current Akatsuki radio science observatory, where we are also looking at data from the Indian Deep Space Network. So on a personal level, Professor Paetzold is a very good teacher, and I believe he motivates the student. I would just like to read out one excerpt from an interview which Isa had with him, and they asked him that what advice would you give somebody who wanted to work in space research? And he said that I would tell them to never give up. Most young people in this field find, while they are studying and pursuing their career, that there are many frustrations and demotivating experiences. And at times such as these, that everyone needs somebody to tell them that it is worthwhile to continue. And just to tell you that he was one of the youngest PI for the radio science experiment when he was selected, and he always motivates his co-workers. And if you are with him for a longer period of time, you realize that he has a very good sense of humor. So with this few words, I invite Professor Martin Petzold to give the talk for today on radio science experiments. Please, Professor.
So good afternoon, and thank you, Varun, for the honors. I have to say that I was the youngest PI 30 years ago, time is running, and I will retire in 2 years, so I'm no longer the youngest PI. But I'm still PI. Yeah, thank you for being here. These have been very interesting 2.5 weeks. I will say some words on that at the end of my talk. But let me start with the talk here on radio science experiments. And Professor Scheele and I, we are having an exchange program with the German Academic Exchange Service. And Professor Scheele was in Cologne with us last year. So I have to show you the view on Cologne, a city which was founded by the Romans as a trading post, and it's over more than 2,000 years old, and dominated by one of the 3 things which you should know about Cologne. First, the cathedral, which is obviously seen here. Then second, the perfume, also called Eau de Cologne. Yeah, Cologne is French for Köln, and which is marked by a number, 4711. This is Cologne. And third, the beer. Maybe you don't know beer here, but if you have ever been in Germany or see something from Germany, beer drinking in Germany, then you see always a big mug, 1 liter of beer. Well, in Cologne, no, this is not the case. In Cologne, the beer, the Kölsch, is served in test tubes. So that is very different. But why I'm showing this photo here also, I want to show you the place where you lived when you was in Cologne. And where is it? The pointer. Here. Yeah. So I have to take off my glasses. You see the church here? Right next was your apartment. And so you see the cathedral here, which is dominating the city, and that is the TV tower called the Colonius. Yeah, so everything is. Cologne people are supposed to be very funny. It's not always the case, but our institute is here behind these houses here, so it's not far from downtown. So you have been there now, and next time you come, you have to test the beer. So I want to talk about radio science, and for all the people in the room, what is radio science? I want to give you some hints in this. First, the name already says is we are doing science with radio waves, yeah, and in this case, we have a radio link between a ground station on Earth and a spacecraft in interplanetary space or in orbit about a planet. And the radio link, there are 2 different radio links. First, the 2-way link. That is, the ground station here on Earth is transmitting a radio signal towards the spacecraft. The spacecraft is receiving it and transponding it phase coherently back on another downlink frequency or even 2 downlink frequencies. So we have the very important term here, uplink and downlink, and we have different frequencies for these. So in the old days, it was done at S-band with uplink and downlink frequencies. Here, these are different for not interfering each other. And then starting in the 80s with the experimental, it is the X-band. Nowadays, it's only X-band, and the S-band is going out of phase slowly. It's going towards the Ka band, which is at 32 gigahertz here. And the other radio link is the stability of the radio link here in the two-way is defined by the ground station here as a hydrogen maser with a stability, relative stability of 10 to the minus 15. When we started the 30 years ago, the Rosetta mission, we proposed for Rosetta many things, and come to that later, but also when ESA was building its own ground station and saying, oh, we have a cesium standard in there. And I said, well, that's not good enough. We need a hydrogen maser. And the person here from ESA was exploding. If you need a hydrogen maser, then you have to pay for it. And obviously somebody talked to him because half a year later, ESA was approving the hydrogen maser in the ground stations. So that is very important. But for the stability of the link, that is noise reducing, but there's also another link, and that is a one-way link. And that means the spacecraft is now transmitting and the ground station is receiving. But typically the oscillator, the standards on board of the spacecraft, we are using here the communication system, practically the radio subsystem, are not good enough. They are even worse than the cesium standard. And therefore, we need to have an ultra-stable oscillator on board. And what you get nowadays in stabilities is in the order of 10 to the minus 13. But this is good enough. What makes matters a little bit difficult is that the contributions to the noise on the radio links is first the thermal noise from the equipment, second the phase noise from the frequency standard, and then the solar wind. Because between the spacecraft and the Earth, the radio waves have to propagate through the interplanetary space, which is filled with the turbulent solar wind. And the density turbulence produces on the radio wave random phase changes because it's turbulence, it's change in density means and in effective index means a phase shift of the radio carrier wave, and a random change means a random phase shift. And that is then seen in the receiver as apparent noise. So the solar wind is increasing an apparent noise in the receiver. And therefore, that is in the order of 10 to the minus 12. And what we don't want is that the standard on board of the spacecraft will become a dominating noise source. So we need something as a frequency standard which is better than what we expect from the solar wind. So then we have as an important thing for the power of the transmitted radio wave, the antennas, the so-called high-gain antennas on the spacecraft, here shown for 3 of our projects, Rosetta, Mars Express, and Venus Express. Rosetta was the largest antenna with 2 meter 20, and Venus Express had the smallest, 1 meter 70. But these are very important devices to amplify the transmitted wave. And of course, what you need is on ground big antennas, because you lose power on the way to Earth. And we are using here the antenna networks from ESA. This is the S-Track ESA tracking network. And on the left-hand side is the 35-meter antenna in Australia. And on the right-hand side is the 70-meter antenna from NASA of the Deep Space Network. ESA as well as NASA have a network around the globe with 3 complexes so that they can track the spacecraft in interplanetary space 24 hours. So applications, what can we do with these radio waves, or what are we doing with the radio waves? So we have several applications here. The first one is the sounding of planetary atmospheres during opportunities which are called occultations. An occultation is when the spacecraft is disappearing behind the planetary disk as seen from the Earth. And then the radio waves transmitted by the spacecraft have to propagate through the ionosphere and atmosphere of the planet. And the radio wave gets changed, get bended here during the propagation and the passage through the atmosphere. And the state of the bending depends on the local state of the atmosphere or ionosphere. So for neutral atmosphere, it means at that point here, temperature, pressure, and neutral number density, which can then derive from the bending angle and via further massaging of the data. You get then vertical profiles in the neutral atmosphere of temperature, pressure, and neutral number density. And in the ionosphere, it depends on the electron density in the ionosphere, and you get vertical profiles of electron density, practically the structure of the atmosphere. So what we observe is then the frequency of the carrier wave transmitted from the spacecraft to the ground. And we are looking for the frequency shift, the small frequency shift on the carrier caused or created by the bending of the radio wave path. And here we have the so-called frequency residuals at X-band, 8.5 gigahertz, already corrected for the classical Doppler, so that we have only the contribution from the atmosphere and ionosphere from the bending, which causes these frequency shift. So you see that is first a variation here. This is all noise from the solar wind. Then we see the change, frequency shift from the main peak in the ionosphere. This is the main peak, the secondary peak, and then it goes down. This is from the neutral atmosphere. And we have here an example from Mars, from the Mars atmosphere. So the neutral atmosphere at Mars gives you an additional negative frequency shift of 5 hertz. In the case of Venus, this would be about 4 to 5 kilohertz due to the thickness of the Venus atmosphere. And then temperature profiles are derived, for example, or electron density profiles. Here we have temperature profiles. Temperature profiles are usually taken to describe the structure of an atmosphere. And this is the case for Venus. We have here 2 temperature profiles for low latitudes and another one for the polar latitudes. See, as further we go upwards in latitude or downwards in latitude to the other pole, there is an inversion more and more pronounced. And this is called the tropopause of the Venus atmosphere. This is here in comparison with a model, an average model of the Venus atmosphere composed from data from Pioneer Venus Orbiter in the 1980s. And we have shown that there are lots of deviations from this model, which is not very precise from that time. We can only access the Venus atmosphere down to an altitude of 36 kilometers, then the atmosphere, which has a pressure at the surface of 90 bars, but at 36 kilometers, it's still 3 bars, and it is that thick that we have critical bending, so the radio wave would never reach the Earth again. It would practically bend around the planet if we would ignore absorption. And we go up to an altitude of about 100 kilometers. We start the derivation at 100 kilometers, where the error in the temperature profiles is about 10%. Then we stop it simply because the error for higher altitudes would explode, and then doesn't make sense. So here the error is about 10%, and the error here at 36 kilometers or at that altitude is in the order of 0.1 Kelvin, so very, very precise. Then above 100 kilometers altitude, there is the formation of the ionosphere. The ionospheres of Mars and Venus, here is Venus, are formed for the main layer, which is here called for Venus V2. V is for Venus. At Mars, it's M2. For the extreme ultraviolet solar radiation, and for the lower peak here, the V1 or M1, it is X-rays and secondary ionization. This is very sensitive on the solar zenith angle, and we see a variation with the daytime and the solar zenith angle as predicted more or less by the Chapman theory, and it goes also with the solar cycle. So we do see changes from solar maximum to solar minimum in the absolute values in the peak densities here. So above the main peak is the top side, the transport region with a diffusion region, and then we have the ionopause, a very steep gradient towards the noise level. Towards the noise level, which is very pronounced here at Venus, not that much at Mars. Another thing we can do with radio science is the sounding of the solar corona at times of superior solar conjunction. That means the planet or the spacecraft is behind the sun at times of superior solar conjunction, and then the radio signals have to propagate through the solar corona. And this is a very dense and hot gas, and there is a lot of phase changes to the carrier wave. And that can be used to study the plasma noise at radio frequencies in the inner and outer solar corona, or what I have called here the hunt for coronal mass ejections. These are common ejections of plasma material outwards, radial outwards, through the solar corona, but to catch them during a solar conjunction of the spacecraft is a rare event. We have some of these rare events, and here, for example, from Mars Express in the year 2004, and we do this at two-way, so we have an X-band uplink and a dual frequency downlink at X and S band, and see then here, for example, for the X-band link, it is very quiet, and then something terrible happens. And we see these large variations in the frequency caused by the passage of a coronal mass ejection. And at the S-band downlink, you see practically the same, but much stronger, about a factor of 4 stronger, because the effects of plasma propagation on lower frequencies are stronger than on high frequencies. And the S-band frequency, the ratio between the X-band and the X-band frequency is about a factor of 4. We can then discriminate for a one-way single downlink here, computing a differential, and can then compute from this the S-band single downlink here, scale it to get an X-band downlink, and subtract it from here and get an X-band, the effect on the X-band uplink. You see there's a shift in the structures here. This is, you have the CME crossing the radio link, uplink and downlink at the same time. But you see it on the downlink first because that comes directly down to the receiver on Earth, while the uplink still has to go to the spacecraft and then coming down, and therefore there's a time lag in there. And we can then discriminate between what has been gotten on the uplink and the downlink. And from that, we have constructed a model from the CME, and I always have described the CME as a bulldozer, which is shifting through the solar corona and pushing everything out of the plasma. And slowly then what's behind the empty void behind the CME is then slowly filled again by the solar plasma from the corona. We can also do mass and gravity field determinations of planetary bodies. And I must say that practically the basic knowledge of masses, though of precise masses and gravity fields, come from these radio science experiments. So we have done several of these experiments. Here's an example from Mars Express. The flyby of Mars Express at Phobos in the year 2008. We have done this 4 times. This one is at a distance of 275 kilometers. And if your geometry is ideal, then you get a shift in frequency after correcting for the regular classical Doppler, which is caused by the attracting force of Phobos on the spacecraft. So the moon is pulling the spacecraft during the flyby to itself, and it alters the trajectory, the flown trajectory, and alters the velocity of the spacecraft. And that leads to an additional Doppler shift, which is shown here. This is the additional Doppler shift. So that here, this difference is practically a measure for the mass and the force of Phobos pulling the spacecraft towards it. And from that, the black line here, black solid line, is a fit model. And one of the fit parameters is G times M here. So we are not solving for the mass directly, but we are solving for G times M. And that is the gravitational constant times the mass of the body. This is the direct result from the fit. We can now divide, of course, by the gravitational constant, but the gravitational constant is the poorest known natural constant of all. And we would destroy the good measurement of a G times M. Not in this case. The error here is about 0.1%. The error of the gravitational constant is about 0.01%. But for example, the mass of the Earth, or the G times M of the Earth, is known to a accuracy of 10 to the minus 9. And if you would divide by the gravitational constant with its inherent error. The mass of the Earth is only known, so real mass of the Earth is only known to an accuracy of 10 to the minus 4, 10 to the minus 5. So that's why we are solving for g times n. And if you are doing these experiments here and you want to resolve a frequency shift due to the gravitational forces, you want to have a certain mass of the body, you want to be close, and you want to fly by slowly. This is not always the case. So I started my career here with a PhD in the mission Giotto. That was 1986, a flyby at Comet Halley. And the spacecraft Giotto was flying through the coma of the comet itself and was decelerated. And this deceleration was not a graduation, it was done in distinct steps. And these distinct steps were caused by dust jets coming out from the comet nucleus itself, and the spacecraft was crossing through. There were in total 2 flybys of Giotto, another one by the comet Scalerup in 1992. But more important is that when I came to Cologne in 1993, in 1995, ESA presented a call for experiments for the new comet mission Rosetta. And we responded to this call with a team which I gathered and asked the people, about 15 team members, and we were selected. And we proposed lots of equipment to the spacecraft, which we needed. For example, an X-band radio link, an ultra-stable oscillator, X-band uplink, and we were selected without anything of that. ESA said, you have to live with an S-band uplink and an S-band downlink. This is what you get. This was terrible, but one miracle after the other occurred. It turned out that ESA wanted to build for this Rosetta mission a new ground station in Australia, the 35-meter ground station in New, which was then put to Norcia in the outback, away from the city of Perth. And in Australia, the cell phone companies were invading into the S-band bandwidth. So ESA had to decide what to do, and they decided to have an X-band uplink and an X-band downlink. So suddenly we got it for free. And finally, we could convince them also to pay for the USO and the hydrogen maser we got also. So in the end, we got everything what we proposed, and we paid for nothing. So ESA was a big success. It was launched in 2004. And had a cruise flight of 10 years to comet Churyumov-Gerasimenko. And in between, ESA flew by 2 asteroids. First, asteroid Steins. This was a small one, and once selected as a target for Rosetta, then all the astronomers went out and observed this asteroid. And what happens then is, from a proposed or expected size of that asteroid of 10 kilometers, longer as more than the astronomers observed, this thing shrank. And that is a common characteristics of these observations. Yeah. So the steins became smaller and smaller, and the distance was enormous. 3,000 kilometers distance was the selected flyby distance. And so, as I said, you want a big object, you want to be close, you want to be slow. That was for Stein, was not given. There was then a science working team meeting at ESTEC shortly before the flyby. And I said, well, if it stays with this size of 6 kilometers, we can see something. Well, the error is about 50%, but at least we have something. And then Marcello Fulcignoni, the interdisciplinary scientist for small bodies, gave a talk and said, Martin, I'm sorry, it became smaller again. It's now 4 kilometers. And this was the end of all this. We couldn't do anything with the asteroid Steins. But there was another one, this one here, asteroid Lutetia. And you see it's a small number, 21 Lutetia. It was one of the very early asteroids ever discovered. And that has a formidable size of 130 kilometers. The velocity, however, is 15 kilometers per second. This is very fast. For example, the New Horizons spacecraft flying by at Pluto, leaving the solar system, had about the same velocity going outwards. The distance was not so important because it was a big body here, and we could get a very formidable signal, a Doppler shift, and a very precise G times M. And there was the discussion, so what is the nature of this asteroid? Is it a C asteroid, or is it P, or is it an M, or is it an X? That X means nobody knows. So the density of that, the bulk density of that is a very important parameter. And everybody was anxious to know what is the density we have determined. And I gave a talk at COSPA in 2010, and the room was packed, and gave my talk. And then I said, well, and the density is, and the entire room was crying, Martin, tell us. So it's a formidable 3,400 kilogram per cubic meter. That means this is close to basalt, what we have here. And indeed, a model of the interior by Ben Weiss, which followed our paper in Science, proposed that that the interior of the asteroid is partially melted and stratified. So that is definitely something we should have in mind for a larger asteroids. But the spacecraft was flying further to Comet Churyumov-Gerasimenko. And you have probably seen, surely seen this comet nucleus before. We called it the space rubber duck because it had the form of a duck with a long body here, elongated body, and a smaller head on top with a neck. And you see the rays coming out here, the fountains. These are coming out of places which are lit by illuminated by the sun. The ice, the underlying ice under the dust cover is sublimating and taking the dust with them. And what we see here is the reflection of sunlight at the small dust particles. So we determined the gravity field of the comet. First the mass and then the gravity field twice. First at shortly after arrival at the comet, and then later when the comet was going back into its aphelion. These are times when the comet is not very active and we don't have these perturbing forces acting on the spacecraft. And so we determined here the G times M, which is a very low value. 666, you should keep this in mind. It's the evil number as written in the Bible. And everybody would say, I told you, comets are coming from hell. And but the surprising point was the density, the bulk density, very low, 500 kilograms per cubic meter. If you think that comets are made up of predominantly water ice and then silicate dust, this is a very low value. And that means that the entire body is very porous. We have a high microporosity in the order of 60–70% of the entire body. And since we have done it twice at the arrival and almost at the end of mission, we have seen that the mass has changed by 0.1%. And we get a formidable mass loss during the passage through the pericenter with the sun. And practically most of this mass loss occurred during these 2 months during the pericenter pass. So we have practically after we have one Rosetta, we have one in radio science experiment on Mars Express. And Mars Express was launched in 2003 and arrived at Mars in Christmas 2003. And that means we have celebrated last year 20 years of launch and 20 years in orbit. And that's the point where I have to introduce my team here. At the time of this celebration of 20 years of launch, one of these persons you have seen, this is Janusz, who was here for 1 month last year in September. And we have here Sylvia, who is my deputy, who will take over when I retire. She is doing neutral atmospheres. Kerstin is doing ionospheres. Sasha is actually doing exoplanets. And Matthias is doing gravity and gravity fields. And but the most important person here is Eddie, our mascot, Eddie the Eagle. So he's practically everywhere with us anytime. And we are very social. On the right-hand side, you see us in the normal social way. On the right-hand side, you see us when you request data from us. Yeah? So be very careful, in particular for the ladies, they have guns. It's of course a joke. We have also the radio science experiment on Venus Express and sounded the atmosphere and ionosphere in about 900 occultations. The large data set is available, and also some of you have shown interest, and you will get the access to the database. But most important of that is what comes after Mars Express, Venus Express. That is currently a fleet of missions to Venus, and one of these is Envision. That was the call, the ESA call for a medium mission, and that was a medium. The M is for medium mission, and was the medium mission number 5. And Envision carries a radar here. These are a radar which can detect then the surface, and also a ground penetrating radar, quite a number of spectrometers, and of course a radio science experiment, actually 2 radio science experiments. So Envision was selected in 2001. It's currently in phase B and was adopted in January that by ESA. That means now nothing can stop us now. So they cannot cancel it anymore. So the launch is in 2032. This is well beyond my retirement. And that means here, Sylvia must and will take over, and that will last until her retirement. So we have here the list of the instruments, and we have two radio science experiments here. First, it's the gravity experiment for the determination of the planetary global gravity field, and an occultation experiment for the sounding of the atmosphere and ionosphere. At two frequencies, very important for the ionosphere, at X band and Ka band. So this is now in phase B, and we are currently submitting our funding contract to our space agency. So there are more missions going to Venus. There are two American missions, Veritas and Da Vinci. Da Vinci is a balloon, I believe, and they are supposed to launch before Envision, but there are currently some delays. And of course, there's the Indian mission where we all hope that that will come to pass. We are all working for that. But the hottest thing currently running in terms of radio science is Lucy. Lucy is a NASA mission to the Trojan asteroids in the Jupiter system, and which is shown here. These things here are solar cell arrays, which span open like an umbrella. And Lucy is named after Lucy. You see the skeleton here. So this is the I forgot the name. Australopithecus. So the early link between the primates and the humans found in Ethiopia in the 60s, I believe, by Donald Johansson. And they were celebrating their archaeological found, and they're celebrating whatever they have done, celebrating, yeah. But in the radio was the Beatles song, Lucy in the Sky with Diamonds. And they were probably stoned and named also the skeleton Lucy. And the idea here is to name this mission Lucy, that we are going to the early solar system. The Trojan asteroids are believed to be the remnants from the early formation of the solar system. So the Trojans are found in the so-called Lagrange points in the Jupiter system, in the L4 and L5 points, running ahead of Jupiter and trailing Jupiter on its own orbit. And the L4 bunch here is called the Greek camp, because all these asteroids are named after heroes of the Trojan War, as told by Homer. And these are named by the Greek heroes, and the other ones are by the Trojan heroes. But somehow the term Trojans stuck for this entire system, and not only for the Jupiter constellation here, but also for others, even for extrasolar planets. So this is the orbit of Lucy, the interplanetary orbit of Lucy. This was launched in October 21. And this is a coordinate system where the line between Jupiter and the Sun is fixed. And then we have two Earth flybys here. Then we have a flyby at the main belt asteroid here, which is named after the discoverer of the skeleton Lucy, Donald Johansson. And then we have in 27, 28, 4 flybys in the Greek camp here. And then there is another round around the sun in 5 years. And then we have a flyby in the Trojan camp at Patroklos and Minutius. This is a big binary asteroid. Both are about 100 kilometers in size. So it turns out that all these 5 or 6 Trojans here are all Greeks. Yeah, so this is the big example. Patroklos was indeed a Greek hero which was killed by the Trojan hero Hector in the Trojan camp. So that's why it's located in the Trojan camp. So it was, Lucy was launched perfectly in October 21, and you see us again celebrating, you know, with everybody here. And then something happened. We had an Earth flyby 1 year later, and then somebody called and said, do you know that there is a small asteroid in the path of Lucy? And 152,830, that's the number of that asteroid. And it turned out it's about 60,000 kilometers away from the Lucy trajectory. And if we invest a small amount of fuel, we could be able to reduce this distance. And this was done. And there was a flyby on November 1st last year in a distance of 400 kilometers. And you see here, Eddie was right at the time of closest approach. And the asteroid was named Dinkinesh. This is also Ethiopian, describing you are wonderful. That does it mean. And so we were very, I was asked, Martin, can you do something? So what's the size of the asteroid? You remember, you need to be close, you need to be slow. This was fulfilled, but you need also a respectable mass. Well, they said it's about 800 meters in size. Made my calculations, and I found, yes, we can get a Doppler shift of about 2 microhertz. The noise is about 1,000 times higher. Okay, you can imagine that this was a no-show for us, for radio science. But then after the flyby, the data were transmitted back, and this was one of the first images here. A very nice image. And then the other came, and there was another one. This thing, this 800-meter thing, has a moon. And the moon was about 200 meters in size. What comes now? Yeah, you look into the images and try to determine the separation distance. And you try to determine the revolution period of the moon about Dinkinesh. And then, as the gods, Johannes Kepler and Isaac Newton tell us, with the third law, you can determine the system mass, and that has been done. And so you see here the size of Dinkinesh, and the moon was called Selam. In fact, it was a 2-lobe moon, like 2 coins which are glued together. Yeah, and as a separation distance is 3 kilometers, a revolution period, 52 hours, and you get a G times M of 32 with an error of about 1%. 32 is the smallest I've ever heard of G times M, and it's 20 times smaller than the G times M of the nucleus of Churyumov Gerasimenko. The density of 2,300 kilograms per cubic meter is something to expect from a main belt asteroid. So this was such a surprise and success very early in the mission. So the hottest part is still coming. And therefore, Eddie loves Lucy. But for the future, and this is what I'm doing, that really occupies me now, is the hottest thing in the future of radio science. That is a new Mars mission for the M7 call, which was selected in November last year for study, for a 3-year study in phase A, and that is MMATIS, which stands for Mars Magnetosphere, Atmosphere, Ionosphere, and Space Weather Science at Mars. And this is a 2 spacecraft mission, and we have there proposed and have run this experiment, so-called MATIS crosslink experiment, macro, a radio link between the 2 spacecraft for the sounding of the atmosphere and ionosphere. And that will be the future of radio science, that you have multiple spacecraft and a radio link between the spacecraft. You get a coverage in the atmosphere, which is magnitudes higher than what you are doing with the current Earth occultations. And yeah, we have celebrated this too, but I have to say that I became PI again in my old days, and I will do this until the end of phase A, when I will retire. And then somebody else has to take over, and that is probably Tom Andert here, which was decades ago one of my PhDs, and he's now the deputy director of the Institute of Spaceflight Engineering at the University of the German Armed Forces in Munich. So this will occupy us for the next 2 to 3 years. We have to develop two transceivers at UHF and X-band, which will then sound the Martian atmosphere and ionosphere. We will use UHF only for the ionosphere. This will give us a huge response, because this is a very low frequency at about 400 megahertz. And we will use the X-band for the sounding of the neutral atmosphere only. And we will get a much higher precision and a much better coverage than ever before. So this is the hottest thing which is currently going. And I would like to thank you for your attention, and also thank you that you allowed me to spend my time here at your lab. I learned a lot here. I learned what a guru is, what Baloo is, and Shere Khan. And I have seen monkeys in free life, and the peacocks here, which are very, very interesting. But I was a little bit skeptic coming here because of the food. Yeah, Indian food is famous for hot and spicy, but this was not the trouble I really had in India. It was the frightening traffic. I try to avoid the cross the street, really. This is my trouble. Good, thank you for your attention, and thank you for being here.
Thank you, Martin, for this interesting talk. Now we can have a few questions.
Sure.
Okay. So, any questions? Yeah.
Hi. First of all, thank you very much for such a wonderful talk. And my question is about the techniques that you have shown is like active remote sensing kind of techniques using radio waves. But there are planets, they have the atmosphere and lightning and all those things. So they may also have broad, radio waves coming from that. So is there any research using those radio waves is happening in your, I mean,
We are here in the microwave bands, about not necessarily for the UHF, but what we have used so far with S-band and X-band. And they cannot be used for lightning detection also for dust in the atmosphere. So any dust particles in the atmosphere, and we know there are some at Mars after dust storms in the higher atmosphere between 30 and 50 kilometers. But this dust is transparent for the microwaves we are using here.
thank you.
That is a question. Yeah.
Thank you, sir, for your informative talk. I have basically two curiosity questions. First one is, how did you get the electron density profile of Venus below V2 layer by radio sounding experiment?
Below what?
Below V2 layer, that V2 peak layer.
So below the V2 layer.
Yeah.
Well, the refractivity profile which you get from the bending. So what you look after is the frequency shift after correction for the classical Doppler. And this goes then from that you determine the bending angle of the radio wave together with the geometry of the occultation plane. This goes into an Abel transform, and the Abel transform gives you the refractive index or the refractivity, the profile of refractivity. And this is very sensitive and precise. And well, everything above 100 kilometers at Venus or everything above 80 kilometers at Mars is solely dominated by the propagation through the ionosphere. So everything you find there in the refractivity is ionization, also electron density.
Okay. Thank you, sir. My second question is, when you talk about size of an asteroid with indefinite size structure, what do you exactly mean?
With size, I mean the diameter. Yeah, we need to be very careful in this because I always make the mistake and take it as radius. But if the astronomers come and say size, they mean diameter.
But
Mean diameter.
mean diameter. Okay. Thank you, sir.
Any more questions? Yeah.
Maybe is molten. So how did you reach to that conclusion, basically?
That is the conclusion from Benjamin Weiss, and that there is aluminium isotopes which do which are was heißt zerfallen?
Aluminum 26. Right.
Aluminium whatsoever.
26.
Aluminium isotope.
26.
And that delivers the heat into the. Yeah.
Okay.
Yeah,
So
and then
No,
it's not fully molten, but it's partially molten.
okay. Thank you.
So Martin, I have one question. This when you consider two satellites sitting on the planet, what should be the geometry? I mean, conditions for the satellite so that we can.
You mean
have-
the orbits?
Yeah.
Yeah, we have here two different orbits, one with a high apocenter at about 10,000 kilometers altitude, and the other one at 3,000. So the orbit planes are also inclined. So they have the same pericenter altitude of 250. And that is about the geometry you need, one very high up the other one average. Um, But you need a sizable distance in between. Yeah. So here we have distances between the spacecraft ranging between 5,000 and 20,000 kilometers. These are the extremes.
So we have a few questions from the YouTube who
Oh,
are
yeah.
watching us live. And the first question is, which type radio waves instruments are used in onboard interplanetary space missions or flyby planetary missions?
What type of?
What type of radio wave instruments?
Oh,
I think
okay.
he is talking about the transmitter.
Yeah, we are using the deep space transponders, which are on the spacecraft for the communication with Earth. So the S and X band frequencies, or now the Ka band frequencies, are actually the communication frequencies for the telemetry dumping to Earth and for the commanding. So this is called the TTNC system, and we hook up with those. Except for the Matisse experiment. That is our own transceiver.
And another question is asked is that how are the frequencies modulated in the interplanetary space mission?
Yeah, this is a digital modulation. That is the data which are dumped to the ground station are in high rate modulation. I believe it is sideband modulation. That is a last cry currently, but I'm not familiar with that stuff.
Yeah, one last.
Wonderful talk. But I have one curious question. When you showed a picture of the asteroid and the dust and then the shining light shining from it very early in your talk, it was all structured. Why should there be a structure in the dust? Like there was more of striations. So what makes it look like that rather than isotropic in nature?
It is not isotropic. It is practically coming all from the side of the comet. It was a comet facing the side which is illuminated by the sun. So it's heated up. The underlying water ice is sublimating and takes away with it. It's accelerated and taking the dust from the comet surface outwards. So we have two components here. First, the water gas, which is accelerated, and the dust particles, which are taken with the heated up water gas, filling up the coma around the comet nucleus. So the nucleus is rotating, and what you mean probably with homogeneous is the further out coma, which is then filled up with gas and dust. And then the gas is ionized, and we have all the other interactions with the solar wind.
Let us thank Professor Paetzold for this interesting talk.
Thank you.
And now I request our director to present a moment of appreciation to Professor Paetzold. Yeah. Please come along. Thank you. Thank you very much, please. So I now invite all of you for a cup of tea outside. Please join us.